and then was created by the Mr. Ujval Gandhi sir. So he is very, I mean, say for, renowned expert in the field of geoscience and remote sensing. A lot of he has contributed through the Google and other application of the GIS. With this, I request uh, Ujjwal Gandhi sir to start your session. Over to you, sir.
Thank you, Dr. Shamlal, for inviting me here and for the kind introduction. Really excited to be here. I hope you can hear me all right. Uh,
Yes, sir. Go ahead.
Great. So already see many familiar names in the group here. So hi to everybody. It's exciting to be here. I want to talk to you about Google Earth Engine today. And I'll start my presentation. It's going to be very interactive demos. Feel free to ask questions. And if you have any discussions point, we can do that during the talk. Okay, so there's a link here displayed. It's a bit.ly/GEE-ML-intro. If you go to this link, it will give you the same presentation that I'm showing. This has got a lot of links. If you have a Google Earth Engine account, you should be able to follow along with me today. So I'll wait here for 10 seconds or so. Maybe you can copy this URL and try to go in your browser. It's bit.ly/GEE-ML-intro. It's not required that you follow along. You have the presentation after the class as well, and you can look at all the links. So everything I'm showing, all the code, all the materials, all the notebooks, everything will be accessible through this link. So this is going to be the lecture outline. I'm going to spend maybe first 20 to 30 minutes introducing Google Earth Engine. Many of you would not have heard of Google Earth Engine or might not have used it. So I'll introduce Google Earth Engine, and then we'll spend some time doing demos. I'll start with some machine learning demos. We'll see how supervised classification is done in Earth Engine, and then I'll show you a recent project worked on for urban growth modeling. And then we'll move on to deep learning with Google Earth Engine TensorFlow, and we'll see how to do a multi-class classification. Before we get started, some clarification on terminology. There are two Google products which sound very similar. One is called Google Earth. This is a very old product from Google, really rich 3D globe. Many of you would have used it to get access to high resolution imagery. And this is a great product, it's for everybody, but we are not talking about that. We are talking about Google Earth Engine, which is kind of a sister product, and it's designed for research and scientific analysis. And this product doesn't have high resolution data. It has got all the public domain satellite imagery, and it allows you to run computation in the cloud to do your analysis. So while the names sound very similar, they are actually very different products, and we are talking about Google Earth Engine today. So when anybody who's done any remote sensing or data science, they know this is how you spend your time. Most of the time you spend is doing data prep, and very little time is then remains for doing the actual research. If you talk to anybody who's done their master's or PhD research, and they say, I spent 5 years doing this, but 4 years was just downloading, preparing data, and then I had very little time to do actual science. So Google Earth Engine was inspired to solve this problem, where you have remote sensing data which is very large in size. We have deep time series of data. How do you make it easy for people to analyze? So we can flip this pie, where we can spend most of the time doing research and not really spending data analysis, data cleaning. So Earth Engine is designed in a way that you have ready access to data that is easily available in a form that you can start analyzing. You don't have to download any data. All the data is constantly updated and it's available in the cloud. And it's designed in a way that you can just specify what you need, the operations you need, and it gets done in real time. And that means your data preparation time is reduced to very minimal, and then you can do data science, where that's what most of the interesting things are. And how do you build a system like this when you want to solve this problem? And do you go and build a desktop software like Erdas Imagine or ArcGIS? But in the big data, when we have living in the age of big data, this kind of desktop-based software doesn't really work, because just to analyze, say, a statewide data for remote sensing, you might have to download terabytes of data locally, and then when you start processing, it may take you months or even longer to even process this data. So downloading data locally, analyzing it locally is not the right solution for big data. So they looked at inspiration from this book, where this book says in the age of big data, it's better to have the data all in the cloud and you ask questions in the cloud. And that's a much better system than asking questions on your local system. So what does it really mean in terms of remote sensing? So the first step in doing this is getting access to the data. So what Google Earth Engine team did is that they got access to all the historic data, all the archive data. So they went to USGS and say, oh, you have all this Landsat data. They caught all the data, downloaded it on the server, and made it available in a ready-to-use form. Similarly, they built pipelines so that whenever new data is available, it gets automatically downloaded to the servers and it's available. That means you have ready access to all the data. You never have to request data, wait for it. It's all available and ready to use. So the total dataset size they have right now is 40 petabytes and growing. Every time I give this presentation, it's grown by like 5 petabytes or so. So it's a huge amount of data that is available on spinning disk. You don't have to download it or wait for it. You just say, I want this data for this time period, and you can start analyzing it. There are 700 data sets. That means Sentinel-2 is one data set. That means every Sentinel-2 image you capture is one data set. There are 700 such data sets, everything from climate data to remote sensing data to SAR data. All public domain data is available in Earth Engine. So once you have this data, what do you do with it? You say, okay, great, I have all the data. Next, you need computing power. You realize that when you're analyzing data on your local machine, you have one CPU or maybe a few multi-core CPUs, and that takes a long time to analyze this data. So what Google did was they said, we'll co-locate computation along with the data. So you can see this could be one of the data centers, and you can imagine that each of the server is having the data locally in the data center. It also is able to compute. So they pulled a large pool of computation resources, and that allows you to use them to do parallel computing on this data. And just think about what might be the computation size that the Google has put behind this. And you might say, oh, maybe I don't know how many CPUs they might have put. They recently announced that last year, the Earth Engine system used 300 billion CPU hours. Just imagine the amount of computational resources that is available to users of Earth Engine. And by the way, did I mention this is free? So as a user of Earth Engine, you can access this massive amount of computation resources for free, and that allows you to run huge computation in real time. So you might say, great, I have all the computers I need, I have all the data I need, now I'll start doing amazing remote sensing stuff. But you said, how do I even utilize this computation architecture? I know how to do analysis on one computer. How do I write parallel computing code? How do I specify my task? And that comes to the last piece, which is the API. So Earth Engine provides an API which allows you to easily specify your task, remote sensing task, and it translates it into the backend to a parallel computing uh, 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 instructions. That means you don't have to worry about how do you write parallel computing code. You just say, I want to get a time series of Landsat for last 10 years, and I want to compute NDVI. And Earth Engine will figure out how to distribute it among all this massive computing power, do this all in parallel, and give you the results back without you having to worry about it. And that is really powerful, because if you start thinking about how to manage this computation resources, managing clusters, writing parallel computing code, that gets really complicated. And the API is completely open and it's available through multiple platforms. So there is a JavaScript-based API that runs in your browser. So now when you're doing remote sensing, you don't need to install any software. You just open up your browser tab and you're ready to go. You also have the API available through a Python notebook. So either through Colab or Jupyter, you can access that. You can also access it via QGIS. I often like to do that, where I can type some code in QGIS and I have the imagery directly available within the QGIS environment. You can also access via R, and there is a Julia API that's recently announced. So again, the idea is that whichever environment you're comfortable with, you can access Earth Engine and do your processing. right? So to answer the question, what is Google Earth Engine? It's a platform by Google to allow you to analyze petabyte scale data very easily. And that consists of the data catalog. You have all the data, remote sensing data available to you, along with massive amounts of computation and an API and some browser-based tools allow you to work with this easily. So that in turn is the entire Earth Engine system. Just a bit to get an idea of how the system works. You see at the top left, this is the, I'm just going to show you. So here, at the top left, you see the request. Here is where you are in a browser or a Jupyter notebook and you say, I want to do this operation. And once you say run, that request goes to the Earth Engine server. So the blue box you can think of is the Earth Engine data center. The data center has a lot of computers. Each computer has access to data. It knows how to do all the different spatial operations, and it says, okay, the user asked to do X for this region, and that computation will get divided across these different machines. Each machine will do a small bit of computation. So you can think of, say, if you asked it to do NDVI for one state, it'll divide into small tiles. Each tile will go to different machine. They'll say, okay, I can compute this NDVI for this very small region very fast. And then all the computers will do this in parallel. The results will get combined and you get the results back. So as a user, what you are getting, you are sending small bits of data, which is the instruction, and you are only getting the results back. You are not getting any intermediate data. So you're not getting the raw data, you're not getting the intermediate product, you only get the result back. Maybe you asked for what is the total area of this class in a particular classified imagery. You only can get a number back. Right? It might have taken a lot of data and a lot of computation to process that, but you're not going to get that. And that means the Earth Engine system is very fast. You can see the results almost instantly because you are not spending time downloading and uploading data. Right? So this is the kind of basic system architecture. I would like to just show you the data, show you Earth Engine instead of talking about it, and that'll give you a little bit better idea about Earth Engine. So if you're following along, you can click on this link and you'll open up Earth Engine. If you get an error saying that your account is not there or sign up for an account, you can sign up. It's a free sign up, and maybe in a day or so you'll get access to the system. So this is Earth Engine. This is Google Earth Engine. This particular environment is called the Google Earth Engine code editor, and you can go to this by going to code.earthengine.google.co.in. And when you go to this URL, you'll see this nice interface where at the center you have some space to write code. You have at the bottom where map results can displayed. On the right side, this is a console where if you ask for a chart or a text result, that get displayed. And on the left, you can save your work. So this is a completely cloud-hosted environment. That means you can do this from anywhere and you can run code. So I'm not going to explain the code. I'm just going to show you, briefly talk through the code and see what the code is doing. And here, I've just written the first bit of code here, which says, give me this one Landsat scene and compute NDVI on that. Right? So when I run this code, you can see that this one NDVI scene gets displayed. You can see this is at the layer is loading, and it loaded this NDVI, this Landsat scene. And you might say, okay, this is great. It loaded very fast, but nothing extraordinary about it. I can do this in my desktop computing system. And you can say, let's just look at the NDVI. And now you can see it's computing NDVI, and NDVI got computed for the entire Landsat scene. And the way this happened, if you saw carefully, you saw the different tiles flowing in. When you asked Earth Engine to compute something, it requires goes in, the server computes that, and you get the results back. And again, this is interesting. You say, okay, I've got the NDVI of this, but then you say Earth Engine has access to Landsat data for everywhere. So why don't I compute NDVI for the whole world? How long would that take? So let's see. So here I have a little bit of code that says, get me all the data collected by Landsat 8 in 2017. And we'll first create a composite. That means you take all the data. Some of this might be cloudy, some of this might be having cloud shadows. So you just take a whole stack of images and do a median composite. And again, this is a very computationally intensive operation, but let's see how Earth Engine does. So I'm just going to say, just create a composite. And you can see Earth Engine has received the request and it's computing those tiles for a global composite, and you can see those tiles are flowing in. And as I'm panning and moving around, you can see the new tiles coming in. And to compute this, it is using 1 year worth of Landsat data and computing this median composite. And you can see I'm not downloading any data. I'm not waiting for it. The results are just flowing in. And that means this is a very interactive system. I can change some parameters and I'll get new results instantly. And now have a global image. Maybe I'll just do a NDVI for the whole world. Let's see how that works. And now you can see I just asked for NDVI for the entire world. And you can see each tile is getting computed and it's getting back to me instantly. And now this kind of changes your whole workflow, where doing data processing and analysis is not in terms of hours or even minutes. It's all instant and real time. And now I've seen many people who'd say their project was to compute NDVI for a state. That's like a 6 months master's project. And now you can do this instantly. That means now focus is shifted to, now I have NDVI, what can I do with it? Can I do some machine learning on that? Can I do some prediction on that? Can I do some interesting research? So now you have this massive computation power at your fingertips that you can leverage to do this at scale. I'm going to show you another demo just to kind of give you a flavor of the different kind of analysis you can do. So Earth Engine also has access to all the climate data, rainfall data, every possible data that you want to use for a research. Here I'm showing one data set called TerraClimate, and this is a very useful data set for climate studies, for water-related studies. Maybe we'll show this demo where I have put a pin somewhere and say this is Bangalore. And I want to get a time series of temperature for last 40 years. And that means to do this in another system, I have to first download the data for 40 years, and then I can get the time series of that. But here, Earth Engine already has the data, so I can just specify that I want this data, I want this TerraClimate data, I want to filter it for last 40 years, and then display a time series of that. So let me just run this. And what's happening right now is Earth Engine server is doing this massive computation, getting this temperature data sets and compute this time series. And you can see on the right side, it took maybe a few seconds, and I've got my time series chart. Let's have a look at that. And this is the monthly max temperature at Bangalore from 70s to 2015. And you can see the individual temperatures here. And if you notice, there is the huge spike here. And I know I was in Bangalore this time. April 2016 was the hottest day in Bangalore, and you can see the data set actually captured that spike. So the idea is that now you can do this long time series analysis very easily. You can do NDVI time series, you can do precipitation time series, and not only at a point, you can say, I want average rainfall for a district for last 30 years, and you can get that instantly. Right? If you're following along, if you want to try something, you can come here and delete this geometry. So I'm going to delete this point, and you can go to anywhere else in the world. So I'm going to search here. This is a search box which allows places. Let's say I want to go to Paris. So go to Paris, and here there are some drawing tools. I'm going to put one point over Paris, and I'm going to run this. And that means that I'm going to get a time series for Paris. Right, so you can do this for your hometown, do this for your study region, and you are able to get this time series very easily. And the same kind of functions can be written for extracting time series for different type of data sets. Okay, so I'm going to start with the machine learning demos. Okay, so yeah, so the metadata is provided by the people who are processing the data, and Earth Engine just provides the same. And there are better cloud processing techniques. If you're working with Sentinel-2, there is this newer technique called S2 Cloudless. And this is a very, very powerful way to do cloud masking, and generally gives much better results. So if you're interested in working with Sentinel-2 and trying to work with clouds, there's this cloudless dataset that was recently added to Earth Engine, which allows you to have a lot of power, and you can mask clouds very effectively. So check out this S2 cloudlets. There is in the user guide, if you search for cloudlets, you'll get the algorithm on how to do this.
Okay, sir.
Okay, so I'm going to move on to machine learning demos. The first one, I'm going to cover supervised classification. Many of you would have done supervised classification, and you would be familiar with the workflow. But I'm going to show you that the workflow that you have in a traditional software that can be compressed, and it can be done so much more effectively in Earth Engine. And this is one of the most powerful applications of Earth Engine. So I'm going to spend some time doing this. Right, so we're going to do the whole workflow where we'll start from scratch, and we'll do the whole supervised classification workflow, collecting data, feature selection, training classifiers, classifying data, and so on. Just as a background, this is what the classification workflow looks like in Earth Engine. You have your input image, you create an image from whatever data sets you're looking for. We're going to use Sentinel-2, but you can use Landsat, Mordis, whichever. You can collect training data, and this could be in form of points, polygons. If you have your training shapefiles, you can upload that to Earth Engine and use that. So you need some training data. Once you have a training data, you can train a classifier. Earth Engine has all the popular classifiers, CART, random forest, and so on. It also has unsupervised classification if you wish to use that. You can then classify the image, and then you do accuracy assessment, say how well the classification worked. And then you tune the parameters, and this is an iterative process where you tune the parameters, look at your results, and once you find the right parameters, and if the results are still not satisfactory, you collect more training data, and you do the cycle. And once you're done with that, and you're happy with the result, you can do some post-processing on the data before you have your final supervised classification. So I'm going to go through this process. This entire workflow, and with all the code and explanation, is given at this link. So I have a course which I teach. It's a live class, 16 hours long, but the whole material for the class is published freely, and all the data, all the code is available free of cost. So if you're interested in learning Earth Engine, you can go to this link and do this. So I'm going to show that course material here. So this is the course material, and we're going to cover this supervised classification workflow. I'm just going to go through quick demos of how the process works, and then if you're interested in learning more or a specific thing that you are stuck on, you can come here and learn more about it. So here's an example of classifying one city in India. So here, say we have Bangalore, and I have the Sentinel-2 surface reflectance data, and I've created a composite for 2019. So this is what 2019 data for Bangalore looks like. And now you say, I want to do a supervised classification. We'll do 4 classes: urban, bare, water, and vegetation. So first thing you need is training data. And collecting training data is a time-consuming task. In the olden days, you had to go and do some field work. But with Earth Engine, you have access to pretty decent resolution imagery, so you can actually see the features in the imagery itself. And you also have the high-res data available as a background. So if I switch to satellite view here, you can see the Google Maps satellite imagery is available here as a backdrop. And that means you can, when deciding which training point to use, you can actually validate that using the high resolution imagery. And that makes the training data collection much easier. Earth Engine provides you some tools here to create the training data right here. So I'm just going to start collecting data. So I click here, and I put one point here. And let me just add some properties. I'm going to say this is an urban class, and I'm going to make it a feature collection. And we'll say this class is 0. So that means all the points I put will have a column called land cover with the value 0. You can change the color. And now I have one training point. I can go and find similar training points in the image itself. And again, a tip for collecting training data, you have to have diverse collection of data. So you can collect all different kinds of urban landforms and use that for training data. And another tip is when you are putting points, always put the points on your Sentinel composite or your the data they're trying to classify. Here is an example. I put the point here thinking that it's urban because the high-res imagery shows it's urban, but we are working with 2019 data, maybe this area was still bad. So if you put a point there, your classifier will think this is a bad line. So you should not put points here. And this is to demonstrate that you should always use the imagery that you're trying to classify as a reference for putting data. And once you have enough points, you can say, I'm going to do a new class, and we'll say this is going to be my bad. New layer, yeah, and it's going to do this is bad, and change it to feature collection, and I'll add a property 1. And that means the value for the output class that we're trying to do is 1. So we have 0, 1, 2, 3, which are the different class names, class values for different classes. And now I can put the bad points. Right? So this is how you collect training data. It's very easy to collect large samples of training data into Earth Engine. And once you have the training data you're satisfied, you can move on to the next step and do the classification. So I'll show you what the classification data looks like. So here I've collected data previously, not too many, just maybe total 30 points or so across the city in 4 different classes. And now you can say I have my points and I can create my training data. And the training data is basically you sample your image and say I have a 12-band image, I'm going to sample that, and you will see your training features. So if I print this training features, you'll see the results on the right. And this is going to be your training features, where you have a feature collection, which is like a shapefile, where each point has an attribute sampled from the original image. And this is the 12 values of all the different bands. So if I look at the features, each feature has this 13 properties. These are the band reflectances and the land cover 0. That means you're training a classifier to say, given this set of 12 values, you can predict that this is land cover urban, and so on. And you can see the other ones where it says if this is the combination of all the 12 values, the land cover is 3. And now you can train a classifier. There are many classifiers available. Random forest is usually works really well. So we're training a random forest classifier and then classify the image. And this is where you see the power of Earth Engine. You're asking it to classify an image with the training points you just collected. You run this and it's classifying the image in real time. As you can see, the data is flowing in and you'll see the results of your classification instantly. And typically in other settings, it's at least a few hours worth of process. And if you have large data, it can be days or weeks. And that means now you can iterate very quickly. You can say, oh, this one looks quite good, but maybe it's getting confused with some bad classes. So I can add some more training points for the bad classes. Maybe you can say, I want to try a different classifier. So just change one line of code, run this, and you have a classification result. And the Earth Engine is a completely open system. So once you're happy with the classification results, you can export this as a GeoTIFF file. It'll go to your Google Drive. You can download it and use it. And that means, if you did the classification, you say, I want to do some other analysis. I want to do some time series analysis in R or Python using some other libraries. Just download the data and you continue working using that. But this workflow will cut down your classification time. It's going to allow you to do interactive classification very easily using the system. I'm going to show some next stuff. And now you say, okay, this is great. But when you start doing it, you might say, oh, I want to do accuracy assessment. So I'm going to show you a demo of accuracy assessment. We have a slightly different area. I'm showing one of the hydrological basins in Bangalore. It's called Arkhavati Basin. And we're going to do even deep learning demo using the same data set. So this data set is a little larger data set. And we want to do classification, but we want to also do accuracy assessment. So we have taken the training data, and you can split your training data. And it's a standard machine learning practice. You have some data set, you split some data and reserve a fraction for validation. Here we are taking 60% points for training, 40% for validation. And now once you have a classified image, You can take your validation fraction, sample that, and say, I know this point is urban. What is the classification result? And you'll get a confusion matrix out of that. So Earth Engine has a method for confusion matrix, and now you can see this particular classification ended up with a 94% accuracy, and this was the confusion matrix. And this allows you to see where the data set got confused, right? So this gives you a baseline to say, I have a baseline accuracy, and I can now do some different machine learning techniques to improve my classification. Before I move on, I want to check if there are any questions. I can't see if you're raising your hand, so just speak if you have questions. Okay, so I'm going to move on. One of the key things that make Earth Engine really powerful for this kind of supervised classification is that the data model of Earth Engine allows you to do put many different bands of different projections, different pixel sizes into a single image. And Earth Engine takes care of projection. That means when you are running your analysis, it will reproject, resample all the data on the fly. And that means you never have to worry about projections in Earth Engine, not worry about your pixel sizes. You can combine multiple data sources very easily. And that means now if you say, I have the raw data, but maybe I want to include some other ancillary data set that will help my training, you can just add it without doing any pre-processing. So let's see an example of the same data set, how we can improve. So the first step in the improving the results is you do a data normalization. So I'm dividing this by 10,000 and you get the values between 0 and 1, which are the reflectance values. And this is usually recommended in a machine learning algorithm where all the data should be in normalized so that the machine learning algorithm is not biased towards a particular value. And here we can say we have the raw bands, but we can help the classifier distinguish different features by adding some indices. And here it's computing NDVI, NDBI, NDWI, and BSI, which is the bare soil index. And it's just adding that as bands. So now if you see at this point, you can see your image and it will have the raw Sentinel-2 bands, but all additional 4 bands with different indices. So now you have band 1 through band 12, and then you have NDVI, NDBI, NDWI, BSI. And now when you sample this image, you're going to get a training feature which has got those values, and that will help the classifier learn from that. And you say, okay, this is great, but maybe I want to use elevation. Elevation is a useful correlation with the classes, so maybe I can want to use elevation data. And that is just 2 more lines of code. You can say there are many, many elevation data sets in Earth Engine. I'll just use right now, there's a ALOS DSM, global DSM 30 meters that's available. We can just say, I'm going to get elevation and slope, and I'm going to add that to my image. And now if I look at my image, it has got 2 additional bands, which is this elevation and slope at each pixel. And you can see it's here. And I didn't have to do anything else about reprojecting, downloading, processing data. It's just there. And now when I sample the image at each point, I'm going to have a training feature which says these are the band values, this is NDVI, this is the slope and elevation, and then this is the predicted class. And that allows you to quickly add different data sets and improve your classification. And this is a game changer, especially when you're working with complex classification where you need a lot of ancillary data sets. And then we can just go ahead and do the classification and see if that helped. And again, all of this will also run in real time using the kind of computation this is doing. It is computing all the indexes, it's computing slope and elevation at each point, and then it's running a random forest classifier. And you can see it's just did it in real time. Look at the confusion matrix, accuracy improved quite a bit. And you can see the results will just start displaying on the map very fast. So these are just some of the techniques for improving your classification. And I worked with many people, and one of the projects I worked on where the team, they said that they had the classification that they were trying to do. It was a country level classification, and it took them 3 months to complete the classification project one time. And by the time they finished, the data was already old. The time had already passed to take any action. And when they implemented everything in Earth Engine, it cut down the 3-month cycle to 10 minutes. Right now, they run this, get the classification results, they get they're exported. So it can really help you make real-time decisions, allow you to shorten your data analysis cycle. The last thing I want to show you is the hyperparameter tuning. This is something that many people ask when you are having a classifier like random forest. How do you decide how many number of trees? In general, the advice is the more trees, the better. But that's not necessarily true. It really depends on your particular training data and the data set you're trying to classify. So how do you select the right parameter? And this is like everything else in machine learning, is you have to try different combinations and see which one works best. So how do you try so many things when, even classifying using a single parameter would take you months, you can't try. But now with Earth Engine, you have this real-time system. That means you can try different combinations and see the results. So this is an example of hyperparameter tuning. We're trying to decide what's the optimal number of trees. So the code says just generate a list of trees from 10 to 150 and just try every combination. So just do this classification 15 times and just tell me what's the accuracy. And I'll pick the number which is the best accuracy. So I'm running this code, and as I'm running this, your computation is split across thousands of machines. They're all computing in parallel, and you're going to get a result which is saying what is the optimal number of trees for the particular parameter. So now I got the result here. And if I open this chart, it says these are the number of trees and this is the accuracy. And if you notice here, it says number of 10 trees gave me the highest accuracy. Like, who would have thought? So now if you just set a parameter 10, you are going to get the highest amount of accuracy. And this allows you to kind of do this in iteration. If you had multiple parameters, you can write 2 loops and say, I want to set the number of trees as well as the bagging fraction. And you can try and optimize for the different parameters. And now you can choose the number of trees as 10, and you have a higher accuracy of your classification result. So I want to stop here for the machine learning demo. In the link that I have, and in supplement, I have a lot of other examples where you can do post-processing or add some additional data if you want to take into account crop phenology. How do you take temporal composites and sample that to create features that can account for crop phenology? I have the PCA. How do you do PCA to extract relevant information and improve your classification? I just want to show you one more example. And this is on to doing correlation, where one of the classification project I worked on, the challenge in classification is identifying different type of vegetation. So here, say I want to identify coffee versus forest. Like, both look green, both have similar kind of reflectances in the spectral band. So how do I distinguish between 2 different classes of vegetation? So here there's a technique where you can say, I can look at the response to rainfall. So you take rainfall for 1 month, say rainfall of January, and you compare it with the NDVI for February at each pixel. So you say, at this pixel, tell me what was the rainfall in January and what was the NDVI in February. And you do this for the entire year. And you have, at each pixel, you have this 12 combinations. And you say, are they correlated? Is there a correlation between rainfall and NDVI? And if there is a correlation, that means that's actually a crop, and because that's having a response to vegetation. If it's a permanent forest, it's not going to, rainfall is not going to affect the NDVI significantly. So this is an example of showing you per pixel correlation using rainfall and NDVI. And this worked really well. This is showing the area in Chikmagalur in Karnataka. This is where all the coffee plantations are. And you can see in this image, we are when we do this rainfall and NDVI correlation, you end up with 3 values, right? Positive correlation, no correlation, and negative correlation. So if you just look at the positive correlation, this is all the green areas. And you can see this is the positive correlation areas, and this would distinguish between the farm and the forest, right? And Earth Engine has these functions where you are able to run this kind of correlations at each pixel of your image, and that allows you to do this. Even you can do, say, regressions at per pixel. You can do trend analysis per pixel, and that allows you to do this at scale. And other systems you have to aggregate it at some unit, but here you can do a per pixel analysis like this. So if you want interested in kind of using different techniques for improving your classification, I have a lot of examples here. And you can see now this one shows all the pixels which have a positive correlation to rainfall with NDVI. So you can look at the script here, and the idea is that once you have this correlation band, just add it to your image and use it for classification. So you have, which I showed you all the bands, sentinel bands, the index bands, the elevation bands. You add a correlation band. And now when you sample that, your training feature will have that. And if there's a strong correlation, the classifier will learn that behavior and say, hey, when I see a positive correlation, that is a farm. When I see a negative correlation, that's a forest. And it's going to allow you to distinguish between those features much easier.